So for this last part of the first lecture group, we want to look at properties of complex and real numbers. Now you probably know these mostly as the properties of real numbers. But because we've introduced complex numbers, these things are true also for complex numbers. So I'll just go real / complex numbers. And what we do is we say that, first off, there's going to be two operations we define. We define the operation of addition and the operation of multiplication. And real and complex numbers are complete under addition and multiplication. And what it means to be complete is if A and B are, again, I'll use complex numbers, but real or complex numbers. So if I have two complex numbers, A plus B will equal a complex number. Some complex number that we'll get through there. Now, it's unique in that if that we call that third number C, A plus B always equals C. You don't have a case where A plus B equals C in one case and A plus B equals D in another case. This would not be unique. And we can say under addition, complex numbers, real and complex numbers, are complete and they produce a unique result. And the same thing, A times B gives us another complex number. And it is unique. It creates a third number. This is what you spend most of your early schooling on, right? You learn your sums and you learn your multiplication tables, and we really build all other operations out of these. So that's the first thing of real numbers, is that the real and complex numbers is they're complete under addition and multiplication. Then in addition, and multiplication are commutative. A plus B equals B plus A. The order we add does not matter. And A times B is equal to B times A. The order we multiply does not matter. So this is able to commute. So that's what we mean by commutative. I think I'm going to switch to a brighter yellow here. Now, we will build mathematical objects that this does not hold true for. And so we're going to look at these things that these mathematical objects do, the numbers, and we're going to use them to kind of help guide us to create other mathematical objects. That's our goal of this course. So addition and multiplication are commutative. And let's see. Addition and multiplication are associative. So if I have A plus B plus C, that's the same as adding A and B first and then adding C, so that we can do associative grouping on it. And A times B times C is the same as A times B times C. So we can, order or pass numbers together on how they multiply. And then there's a distribution property. where A times B plus C is equivalent to AB times AC. We can distribute. And so all real and complex numbers exhibit these properties. There's also some things that we can define about the elements in them. There is, we call this the identity for addition. There's some number that we're going to call 0, that when I add it to a number, I get the number back. And there's the identity for multiplication. There's some number, which we call 1, that when I multiply it by some number, I get the number back. Also, related to this is we have the additive inverse. There is some number that's the additive inverse, or negative of A, that when I add it to A, I get 0. And for multiplication, again related to this, there is a number which we call the reciprocal of A, that when I multiply it to A, I get 1 back. And so, right, this is the reciprocal, and this is the additive inverse. And let's see here. That is the properties that we can use to make other rules. And these are all we really need to really build algebra. So for example, we have this idea that A over B plus C over B, well, we have a common denominator, so we add the numerators. But how do we know this is true? Well, what we can do is we can start with our left-hand side here, and we can apply the distribution rule in reverse. So 1 over B can be pulled out front, and then I get A plus C. And then in how multiplication of fractions work, that comes upstairs. And so these flow naturally into each other, that this comes across. And we use many similar rules. We can even, let's do it with an actual number. If I have different denominators, so I have 3/5 plus 2/15, we said, hey, we want to find a common denominator. And we go, hey, it'd be nice if this was 15, so I multiply that by 3. But if I were to just multiply this whole thing by 3, I change the value. So we use the identity, we multiply it by 1, so this has the same value, it just changes the way it looks. And so that's how the properties of complex and real numbers come to help us build other rules. And all of algebra is really kind of combining these rules into little machines that do work for us on the patterns that we work with. Our goal in this class is we're going to be working with not numbers, but vectors and matrices. So we have to abstract what we got from the properties of real numbers. And so we're going to call these the field axioms. And these are things we're going to use on different objects that we have to do algebra with. And so we're going to get some notation here that gets rid of us talking about the sets of numbers, and we'll be just talking about sets of objects, and we will let different objects fill in these roles as we progress, specifically different sets of matrices and different sets of vectors. So we'll say a set of objects which we're going to call S form a field under two binary operators. And those operators are going to be something that resembles addition, right? We get to define how it works, but we'll say it's the addition, and multiplication. Again, because we're not doing these numbers and putting a circle around it, provided that and we're going to have some restrictions for this to make a field. The set forms an abelian group under addition. And what that means is if X exists in my set and Y exists within set S, then X, whatever we've defined the addition operator to be, also exists in group S. So the idea of the abelian group is that when we perform, however we define this addition, we get a number that's still within, or not a number, an object that's still within our set. Just like when we add complex numbers, we get complex numbers back, or we add real numbers and we get real numbers back. Then in, however I've defined this binary operator, it's commutative. And we'll say for all X and Y that are in my set. So X added to Y with our new definition of addition equals Y added to X. So it's commutative for all X and Y that exist within our set S. Right? It's also associative. So X, my additive operators, and that's true for all X, Y, and Z that exist within our set S. So what we've done is we said, hey, if we're going to form a field, it needs to be complete under addition, just like our real and complex numbers were. It needs to be commutative under addition, just like our real and complex numbers were. And it needs to be associative, just like our real and complex numbers were. Let's see, that's C. 1D. X contains an element and we usually bold this. It's a zero-like object in our objects, such that when I perform my newly defined addition of this zero-like object, I get my original object back. And this is for all X that exist within S. Now remember, this looks exactly like the properties of complex and real numbers, but the sets we're going to use are not going to be numbers. And so it's going to be the definitions of the additions and multiplications that satisfy these rules that we're going to focus on for our new objects. And let's see, then in to every X that exists in our set, there is an element negative x that exists within our set such that x plus negative x equals that special zero thing we've created. Alright, so that's the additive rules. And let's look at the multiplication rules again for whatever object we want to make a field out of. So the set of every element except 0. And the same thing kind of happens with real and complex numbers. Because we can't divide by 0, 0 can't be a multiplicative inverse. So when we describe multiplications, we really exclude 0. And the same thing is going to happen with the objects that we create in our new special zeros. And so they'll form an abelian group, so they'll be complete under multiplication if x exists within our set and y exists within our set, then x, however we define multiplication, times y exists within our set. There will also be commutative under multiplication, and we will find things that don't satisfy this, and there will be some things we'll have to do specially because of that restriction. And for every xy in our set. And I'm going to continue. It's also associative. For all x, y, and z in our set. And 2D S, our set S contains an element one, which does not equal the 0 element. Now, because we're defining these objects, there's a chance that we can have a mapping like this. So for these rules to be true, we have to exclude that one element doesn't equal 0. With our real numbers and their creation rules, the real and complex numbers with our creation rules, we didn't have this problem. 1 didn't equal 0. But because we get to define the sets we're working with, and we get to define the operations on them, we need to be aware that this cannot happen. And so such that one element times x equals x. And we'll bold this so that it's not the number 1, it's the element within our set that has the property 1. And that's for every x that exists within our set. And if x exists within our set and x is not the 0 element, there exists one element one over x in our set such that x times 1 over x equals 1. And a lot of our work will be defining these rules so that we can manipulate different objects. And in our case, it will be matrices. And then in 3, that unifies these, we have a distribution rule that gets defined with our operation. And that's for all x, y, and z in my set. So what we've done here is we've kind of taken what we know about number, complex number, and we said, okay, if I want to do everything I did in algebra with something that's not a number. If I want to do it on other sets, then I have to define addition and subtraction, or addition and multiplication, in such a way that these things are true. And it's a very freeing thing for mathematics. It makes mathematics a thing of sets, but it means that we kind of have to be careful in the things that we create. All right, so we're set up. We've kind of have what the set of numbers do for us. In the second lecture, in this portion, we're going to look at the problems linear algebra is trying to solve and the sets of objects that we need to create to do that.